Good day to you all. Welcome to this first of the online lecture series. In the interest of time, I'm going to go straight to the topic. We are going to be looking at AC circuit analysis techniques. Specifically, we are going to consider node analysis and loop current method. These two techniques are based on the well-known laws of Kirchhoff's current law and Kirchhoff's voltage law. Please note that what we learned in electrical engineering 1 when we were dealing with DC circuit analysis applies to AC circuit analysis. We only have to know that in place of DC sources, we are considering AC sources, which are represented by phasor voltages or phasor current sources. And in terms of the resistances, we have impedances, which have got real and imaginary parts. To the second slide. This is just to remind us how we handle complex numbers, because you will need to add impedances. For example, if they are in series, you need to subtract, you need to multiply, impedances with current complex on phasor form. If you are going to apply Ohm's law to divide voltage with impedance, it's like dividing two complex numbers, how you do it. And also at the end here, if you are going to take the conjugate of a complex number. So this is just a revision, just to refresh it and make sure you understand. Now, circuit terminology. I've got a network here with 3 sources and a number of elements which are labeled Z1, Z2. These are impedances. Now first, let's talk about mesh and a loop. What is the difference? What are they? Now you'll notice that this network, what catches you in the eye, it's got like 4 windows. 1, 2, 3, 4. These can be regarded as window panes. Of course, if you follow my pointer, that there can be regarded as 1/2 of the window, which has got 2 panes. The same here. If I go around like this, of course I'm following the full window. Now this here, if we form a closed path indicated by that purple line, that in the language of circuit analysis we call it a mesh. A mesh is a closed path which does not contain any other loop. If I create a loop which goes around like that, the direction of my pointer, my mouse, then this loop actually has got 2 other loops inside it. So that is not a mesh, we call it a loop. I can create one loop by going through the outside of, right through the, the perimeter of the window, if you like, right round like that. Then that's one big loop. It's not a mesh. Alright? Then you'll see here I've got dots. These we call nodes. the point where conductors carrying current through the various elements meet. So this is node 1, this is node 4, they are labeled these nodes. So the path between any two nodes is called a branch. Now these nodes have voltages. So it's normal practice to call the voltage according to the numbering. So the voltage at node 1, I would call it V1. At node 2, V2, and so on. Voltage we measure with respect to 2 points. So in most cases, we choose one node to be the reference or the ground. And this symbol here emphasizes the point that node 1 is ground or reference node, which means it is at 0 volts. So there is a closed path we call a loop or a mesh. There is a node, a point where two or more current carrying conductors or branches meet. There is a branch, and of course there are sources. The Kirchhoff's current law and the Kirchhoff's voltage law are summarized in this slide. We know that the total sum of currents that flows into a node is 0. By convention, we take currents entering to be positive and those leaving the node to be negative. For a closed path, the total voltage drops. The total voltage drops in a closed path is equals to the total voltages of the sources, voltage sources. Right? Now this we have met in Eng 1, so I'm sure you are familiar with that. Now let's quickly start talking about node analysis. What are we trying to do when we're talking about node analysis? Now, if we are given a circuit like the one that you have seen here, I'm projecting again, you might be interested to know what is the current flowing in that branch. What is the voltage at that point, and so on. Now, analyzing this circuit to get the values of those various quantities is what circuit analysis is all about. Now, there are various techniques that we use, and the first one we are going to start with is the node analysis technique. Because if, for example, I'm looking at this circuit, if I know that voltage and I know this voltage, I can determine from Ohm's law what current is flowing in that branch, because it's just this voltage less that divided by this. So we follow through a number of steps which are outlined here. I will not read, but rather illustrate them straight to the problem. Example. So here we have got a circuit. The first thing is we identify the nodes. I have labeled the nodes with the voltages. Remember, node 1, the voltage is V1, node 2, the voltage is V2, and so on. So I have V1, V2, V3, V4. And for each branch, I indicate a current. The direction is arbitrary, the one that you choose. So I've indicated all the three currents here flowing into the node. Another important thing to note is that the voltage V2 is actually 100 volts. The node voltage V4 is 75 angle minus 10 volts. And the voltage V3, because the polarity shown in the circuit symbol for this source is minus 50, right? Angle 30 degrees. So these three voltages are known. So we are basically down to one voltage, which we do not know. That makes our life easy. And let's start by writing the KVL equation at node 1. Let me go to... Okay. The first equation that we write here is the summation of the three currents. They are all flowing into the node, so I1 plus I2 plus I3 gives me 0. And that's the only equation that I need for this. The next step, I must apply Ohm's law in each of those branches to calculate the currents. If I go back, if I want to find I1, then I1 is V2 less V1 divided by 20 minus J, 30. So that gives me this equation. And the same way I find the expressions for I2 and I3. Now once I've got these expressions here, I can now substitute into this equation and I obtain this equation here. I've just substituted for V1, V2, V4 and V3. Now if you look, this is just a simple equation in one unknown, which is V1. So what we do is we simply manipulate this by dividing and grouping all the like terms in V1 and those that are independent of V1. And finally we arrive at this step here just by simple division. Now most calculators, you can punch this whole expression there and then it will give you the answer, but I chose to do it, a step at a time. So I'll do one term at a time and it gives me this, and from here I get the final answer for V1 as 87.9 angle 65. Right? So this is all that I need. If I wanted my three currents, I can now take this voltage back into each of these three equations to find I1, I2, I3. I'll leave you to do that. Let's look at another example. Now this one is an interesting example. It is interesting because there is a new voltage source that is introduced here. The diamond symbol is used to indicate a dependent voltage source. Dependent means it depends on voltage or current in some other part of the circuit. In this case, it is depending on the voltage indicated Vx. Let's go to the next slide. You see I've put here a blue arrow to indicate Vx. Now, we need to label our nodes. We have node 1, and this is not known, So I've called it node 2. There's two elements meeting here. Remember, this is a node because there's two elements meeting, the capacitor and that resistor. Now when it comes to writing your KCL equation for this circuit here, the dependent sources, you can just regard them as independent. In other words, they don't really, change the way you write your KCL equations. So we have defined our nodes 1 and 2, and really we need to write the KCL equations for these two nodes. I've also indicated the directions of the currents in all those branches. Alright, so next slide. I'm now going to write the equations for node 1 and node 2. Now node 1, you will see that the direction of my current flow, the current here would be V1 less 1 volt from this source, divided by 4. Right? The current for this branch here, because it's in that direction, it would be V1 less this voltage, which is this voltage, or V out if you want. So it's that voltage minus, right, 100 Vx, right, divided by that impedance. And the current in this branch is simply V1 divided by 0.16. And in that branch, right, remember this is flowing in, so it would be V2 minus V1 divided by that branch. We put that all together, it gives you that expression. Another thing to note in this particular example here, I go back to the previous slide, is you'll see that the node voltage V2 is indicated by the arrow, the polarity thereof. But this V2 is the same as Vx, only that they are opposite in polarity. So in other words, the V2 is actually minus Vx, or the other way around, or Vx is minus V2, and therefore you take away this Vx here by substituting by minus V2. So that whole equation there simplifies to this. After some manipulation, there is two unknowns there, V1 and V2. That settles it for node 1. Then we go to node 2. Node 2, if I may go back to the circuit, you see at node 2 we have got two currents and they are flowing away from the node. So if we have V2 minus V1 divided by this plus V2 minus 100 Vx divided by 80, add those two, you should have 0. Right? This is what we have. V2, my negative is missing here. I don't know what's happening to the equation editor, but it's V2 minus V1, and here it's a V2 minus 100 Vx equals to that. Again, the same relationship connecting Vx and V2, we substitute it here. So that second term there changes to V2 plus 100 Vx. Again, you simplify group-like terms, you end up with this nice equation. Now we have got two simultaneous equations in two unknowns, V1 and V2. The next slide, we simply choose to put these two equations in a matrix form. you can solve them by way of simultaneous equation, where you do substitution and elimination. Just like if you had two simultaneous equations in x and y. Like, for example, you have ax plus by equals to something, and then cx plus dy equals something. The same method of solution is what you do. Or some people may choose to evoke Cramer's rule. If you remember Cramer's rule from maths, you can also use that, right? I just put these numbers into MATLAB, and it gave me the answer. But these are 2 by 2 matrix you should be able to do manually, in case you were required to sit an exam or a test or an assignment, as the case is going to be now. So that's basically the second example. Let's look at another example. Again, this one has got a dependent source. That one, the diamond. And it has got 2 node voltages, which are already indicated, V1 and V2. And the impedances of the various elements are similarly indicated. The current source over this side is indicated in the time domain. In phasor form, that is 10 angle 0, as indicated on the diagram below. So I indicate the directions of my currents. I did not put the labels of the currents because now I understand what I'm doing. So I only show the directions because I want to write the KVL equations at node 1 and node 2. Therefore, I proceed. At node 1, watch that at node 1 we've got a current source. So this entire current, according to KCL, this is flowing into the node, and these two are flowing out of the node. So it means that current is equal to this plus that. So that current is V1 less V2 divided by that. This one is simply V1 divided by 2, which is what we have here. And the second stage is simply simplifying that, grouping like terms in V1, just make it neat. And we do the same for the first node, second node. Now you'll see that here the current in the inductor J4 ohms is outflowing, and the other 2 currents are flowing in. So it means this current plus that current is equals to this. Alright? Now, this current here is simply V1 minus V2 divided by that. This current here is simply 3Vx, right, minus V2 divided by J4. Now notice that here Vx is the same as V1. So when you say 3Vx, you can substitute Vx by V1. Alright? So we go to the next slide. There we go. Alright? The Vx is equal to V1. So we make that substitution, and then we simplify, and we get those two. So the equations that we need to solve in this case is this equation here, number 2, and that equation number 1. Again, you can simplify this using the method of simultaneous equations in 2 unknowns, or you can assemble these 2 equations in a matrix form, and you use Cramer's rule, which is illustrated here. If you happen to have forgotten Cramer's rule, you can send a request. We can meet, and I will explain it by illustrating it in more detail. But I'm hoping that these are techniques we learned in our maths or you should be able to remember. Right, these are some advantages for node voltages analysis. Of course, it gives you the voltages. If you have got current sources in the circuit, it makes your life easy. It is good when the few nodes in the circuit, and it works for any circuit. So that is the node analysis technique. Let's go to the mesh analysis technique now. I will try to be faster. Now, the mesh analysis technique works on the basis of Kirchhoff's voltage drop law. How does it work? We have already explained what we call a mesh. That's a closed path which does not have any other loop inside it. Alright. But for the circuits that we are going to be dealing with, in general, we tend to use those two terms, mesh and loop, interchangeably without drawing that much distinction between them. But just remember, a mesh does not have a loop inside it. Alright. So the steps, again, we are going to illustrate them by way of example. Now there is a circuit. Again, it has got two windows, two meshes. The mesh current is this current which flows round like that. Right? Now notice that when I was dealing with the node analysis, I was indicating the current flowing in the branch, and sometimes those are called branch currents. Right? But here I'm talking about the current circulating in that loop or in that mesh, which I have taken to be clockwise. And I'm also looking at the mesh here clockwise as indicated by that arrow. So we have two mesh currents here. So notice that here in this element here, the current flowing in that element is this mesh current I1. In this element 40 plus J20, the current that flows here is 40 plus J20. Then the current that flows in that mesh, this is where sometimes there's a little confusion, is an arithmetic summation of these two. This, with respect to that, this current is flowing down, but this current will be flowing up opposite to this. So the net current in this, when we are looking at the mesh 1, will be I1 less I2. Alright? Now, I've used the red arrows to indicate the polarity again of the sources as they are given, just to emphasize. If you look at this source here and that source, if we follow the direction of this mesh, these two sources are helping each other. So the voltages compound, they add, alright, positively. So the net voltage source in this mesh is actually 100 plus this voltage, which is this equation here, the left hand side of it. The other side is going to be the voltage drops now. So it will be this element, or that impedance, 20 minus J30 times I1, which is this term, plus that impedance times the net current in that direction, which is I1 less I2, this current. So that's the first equation for the first mesh, mesh 1. For the second mesh, again, you follow the direction that I've given for the current, right? Now you will see that if I follow this direction here, these two voltages, as they are indicated by these polarities here, they are counter to the direction of I2, and therefore I negate these two voltages because I want to follow this which I've indicated. So I'll say minus 75 angle minus 10 minus 50 angle 30, so I add them here. Alright, then I have to do the voltage drops. First, it's 40 plus J20. The only current here is I2, which is this. Oh, sorry, there are three impedances in series. It's 40 plus J40 minus J15 times I2 plus J40. The net current in this direction in this instance now becomes I2 minus I1, because I1 is opposing I2. That. So these are the two mesh currents. The next thing is we simply simplify them, collect like terms together, so that we have got our nice two equations in terms of I1 and 2. So these two equations can be simplified by substitution and elimination, by which I mean you can express I1, use one of these two equations to express I1 or I2 in terms of the other, then take that expression and plug it into the first equation so that you eliminate one of the two variables. The resulting equation will only have one unknown, and then you proceed to simplify it. Multiply, divide until you get your answer. That's where you need to be very careful because of the complex numbers. The chances of making mistakes or any calculation errors are very high. Or if you want, you assemble this into matrix form, and you can use Cramer's rule again to solve for I1 and I2. I put it in MATLAB, but you must be able to do it manually, at least for these 2x2 cases. Then you get those answers. Now this is a second example to illustrate mesh analysis. Now there's something here which I need to point out. Now when we look at this circuit, automatically we can see that there are three meshes. Follow the pointer. It is that mesh here. Right? 1. And then it is that mesh here. 2. Then that mesh here. 3. So I've indicated the currents in the circuit below. This is mesh current I1, that's mesh current I2, mesh current I3. If you want to apply Kirchhoff's voltage drop to mesh 1, it's quite easy. There is 50 volts there, equals to the drop here, which will be 10 times I1. Then the drop here, it will be minus J4 times the net current here, which will be I1 less I2. And similarly for this, you are going to get the drop here as 5 times I1 less I3. So that's for this mesh here, the equation, KVL equation. But when it comes to these two here, there is a current source in between. You can't do Ohm's law here. You see, there's nothing to say you can multiply current in this impedance. No. What we do is we create what we call a super mesh. We take out that source, and there we have taken it out. Now we are going to look at this mesh, right? That's your super mesh, the dotted line. I'm still going to use these currents, the dotted line there. Alright? If we apply the KVL equation to this, we can write the equation for that. Now the only thing which we need to note, as I have said, is the currents that are flowing there, right, and here. The red arrows that I've put indicate the current I2 and I3. So when you come to do a KVL equations for this super mesh, there is no source, so it's 0 is equals to. When you look at this, the impedance is minus J4, but the current, this current here is counter, it's opposing this. This is this red arrow. So the net current in this direction for this impedance is going to be I2 minus I1, meaning that the drop is minus J4 in brackets I2 minus I1. To that, you are going to add the drop across the J8 impedance. And of course, here there is no other current, it's only I2. So it will be plus J8 I2. Then you need to add the drop here. Again, in this impedance minus J6, the only current is I3. So it's minus J6 I3. When you come here, you have got I3, which is in this direction, and you have got I1, which is opposing it. So the net current there will be I3 minus I1. So the drop here will be 5 in brackets I3 minus I1. So those four drops you add together and equate them to 0, and that gives you this equation here. Alright? And after that, we are back to simple, simplification of the equations. Another last equation which I need to bring your attention to is, because remember there are 3 variables, but so far we have done a mesh equation for that, and we've done a super mesh equation here. We are short of one equation. But if we go back to this circuit here, you will see that I2 is flowing in that direction, and I3 is in the same direction as the source current, the one I'm pointing at, 2 amps. Therefore, I3 minus I2 is equals to 2. That gives us our third equation. So we can use this equation now to eliminate I3 from the first 2 equations. And once we eliminate I3 from the first 2 equations, we have got 2 equations in 2 unknowns, I1 and I2, which we can assemble as before in matrix form, or proceed to simplify using elimination. And since we are only required to find I0, I've used Cramer's rule here, and this is what you get for your answer. Then we are almost home and done. Take out that. Now there is no example here, but this is just a simple one to illustrate the branch current method. Now, like I've said before, here we are actually using KVL, but instead of defining the loop currents, we define branch currents, and we stay with the branch currents. So you can see here I've got this branch current equation. That's a KCL at node 1. And then these are the two equations here. This is just KVL equations in that loop and that loop. And then I can use this to eliminate I3, and then, now if you compare this technique with the node analysis technique, you'll see for a similar circuit. In the node analysis technique, this circuit here will only have one unknown, which will be V1, but here we end up with two unknowns. So this really is not an advantage compared. The nodal analysis is an advantage over this. It reduces the number of unknowns. With that, I want to thank you and wish that this can be of some help. Please try and do the TATs. God bless you.